Alright, in this video here we're going to talk about the transformations of the sine and cosine graphs. Alright, so I put up here at the top just the basic graphs of the sine and cosine functions, just one period of those graphs. Now if you haven't watched the videos that I did on the graph of the sine function and the other one I did on the graph of the cosine function, I would advise watching those before you watch this one. If you understand why the graph of the sine function looks like this, why the graph of the cosine function looks like that, it's going to be a lot easier to comprehend all the stuff that we're going to talk about in this video here. Right? So the sine function, just real quick, remember the sine function, the period is 2 pi, which means it's periodic, meaning that it repeats the same behavior over and over again. So the sine function starts at the origin. It doesn't start at the origin because it does continue to the left of the origin through negative x values. But for the one period of it starts at the origin, then it goes up to a maximum height of 1, back down to 0, down to a minimum height of -1, and then back to 0 for the end of the period at 2 pi. And then it just repeats that behavior over and over and over again. All right, and it does that the same in the other direction as well. All right, so that's the graph of one period of the sine function. And then for the cosine function, also has a period of 2 pi. The cosine function, though, starts in a different spot. Right, the cosine function, or the one period of the cosine function starts at 0, 1. Right, it doesn't start at the origin like the sine function does. The cosine function starts at the maximum value. Right, the sine function starts at the middle value of the graph. The cosine function starts up at the maximum value. So the cosine function starts at 1, then comes down through 0, down to -1, back up through 0, and then back up to +1 at 2 pi to complete that first period, and then it continues those same values over and over again. So it's the same graph, just kind of cut and paste or copied and pasted over and over again in both directions. Right, so if you look at more than one period of the sine and cosine functions next to each other, they look very similar. They're both curves that go like this. Right, they go up and down between +1 and -1, and they do that forever. It's just that they start at different points. So when you look at one period of the graphs, they look different from each other. But when you graph the whole thing out, they're basically the same graph, just one of them shifted over a little bit from the other one, right? Because that starting point is shifted over a little. All right, so those are the graphs of one period of the sine and cosine functions. And again, if you didn't watch the videos where I explain why those graphs are what they are, you should definitely watch those so you understand where that all comes from. All right, now, the formulas for the transformations of the graphs of these functions. They look pretty complicated, but I'm going to show you how it relates to things that we've done before. All right, so y equals a times sine of k times, parentheses, x minus b plus c. And then the same thing for cosine. This is the same formula here, it's just a cosine instead of a sine. Right, so the rules for the transformations, it's the same rules no matter whether you have a sine or a cosine. It's just that when you have a sine or a cosine, you're starting from a slightly different parent function. Right, these are like the parent functions here, and then these are going to be the rules for how to do the transformations of those graphs. Now, if you recall, like one of the videos I did a while ago was about transformations of graphs of functions, and we did transformations of graphs of like the quadratic function x squared, and the square root function, and absolute value, and there's a couple others that were in there. And we talked about the rules for shifting horizontally left and right, shifting up and down in the vertical direction, stretching and shrinking vertically, stretching and shrinking horizontally, reflections, flipping the graph over in either direction. So if you recall all the rules for those transformations, these here are the same rules, right? We give them different names when we're dealing with trigonometric functions, just because of the wave nature and the periodic nature of the graphs. We give some of those things special names, but the rules are exactly the same as far as where you put numbers and how they affect the graph. Is the same as the rules for transformations that we talked about with other types of functions previously. Right? So if you don't recall those, look for the video that I did where I talk about the transformations of graphs. I actually did a bunch of different videos for each different rule of transformations. I did one for horizontal shifts, I did one for vertical shifts, and so on. So you can watch those videos and kind of get those under your belt and understand how those work. And then for the trig functions, we're just using the same rules. We're just giving some of them slightly different names, which apply specifically to trigonometric functions. All right. So first thing, that number in front of the sine or cosine function, the a. Right. Well, if you recall from the rules of transformations, if I multiply my parent function by some number, that's going to be a vertical stretch or shrink, depending on if that number is bigger than 1, it's going to stretch it out. If the number is less than 1, it's going to shrink it down. Right. So multiplying that number affects the vertical direction, stretching it or shrinking it. Right. Same thing here. but we call that the amplitude for these trig functions, for the sine and cosine functions, right? So when we talk about amplitude, since the sine and cosine functions, both of the graphs are waves, amplitude refers to the height of the wave, right? So if you ever taken a physics class or anything like that, amplitude refers to the height of a wave, no matter what type of wave you're dealing with, right? So for the A, if it was 2 times sine of t, well then instead of going up to 1, it would go up to 2, and it would go down to -2, right? It's vertically stretching out the graph when I multiply it by a number that's bigger than 1. If I multiply it by a number less than 1, like 1/2 sine of t, well then the maximum point is going to be 1/2, and the minimum point is going to be -1/2, and it's going to shrink the graph down, right? So that number in front, we call that the amplitude. That determines the height of the wave. It's the vertical stretch or shrink that we talked about with the other functions that we did previously. All right, so that's our amplitude. The number multiplying the x inside the parent function, that's going to affect, just like with other functions, our horizontal stretch or shrink. Now, for the trig function, since sine and cosine are periodic, that k value itself doesn't determine exactly what, or that k value itself is not the value of the horizontal stretch or shrink, but that helps us determine the period of the graph, right? So the normal period for sine and cosine, remember, is 2 pi. Well, if I have a number multiplying the x, right, that k value there, the period is going to be 2 pi divided by that k, right? So that's kind of the hardest part of doing these types of problems of graphing the sine and cosine, is determining the period and remembering that little formula. You just have to remember what that formula is, right? So if there's a number multiplying the x, that's going to be a horizontal stretch or shrink. But with the sine and cosine functions, if I stretch it horizontally, I'm stretching out the period of the graph, right? If I shrink it, I'm shrinking the period of the graph, and it goes by the formula the period is going to be 2 pi divided by whatever that number k is. All right, the B is the horizontal shift, right? A number that's inside the parent function that's being added or subtracted with the x shifts the graph to the left or to the right horizontally. Same exact rule as what it was with the quadratic function or the square root function, right? The number inside the parentheses or inside the parent function with the x added shifts it left or right. And remember, it's the opposite of what you think. So that the formula says x minus b, the horizontal shift is positive b, right? So if it's x minus a number, we're actually shifting the graph to the right. If it's x plus a number, we're actually going to shift it to the left, all right? The C, the number that's added or subtracted outside of the parent function, outside of those parentheses and brackets, that's going to be our vertical shift. Right? Again, same rule as what it was for other types of functions. If I add a number to the outside of the parent function, it just shifts the graph up or down. Right? So that's our vertical shift, is that C. And then if I have a negative in front, if my A value here is a negative number, well, that negative in front flips the graph over. It's a reflection in the x-axis, which is flipping it in that vertical direction. All right, so those are the basic rules for the transformations of the sine and cosine functions. Again, they relate directly to all the rules we talked about previously with other types of functions. So if I went through that too fast and it didn't quite make sense, any of the things I said, like the vertical shift or the horizontal shift, go back and watch the videos that I did for other types of functions where I explain those rules. Like I did one entire video just talking about vertical shifts. I did another one just talking about horizontal shifts. So if you want to review those, it might be a good idea. What I'm going to do here is pause this recording, erase all these rules. I'll probably leave the parent functions up there so we can use them, but I'll erase all these rules, and then we'll look at probably one example on this video of graphing one of these functions with these transformations, and then I'll do another video where we do a couple more examples. Alright, so I'll put up here an example of a trig function, a sine function that we're going to graph involving some transformation. So it's y equals sine of 2 times parentheses theta plus pi. Alright, so first thing, this symbol here, theta, is like a 0 or a circle with a line going through it. That's the Greek letter theta, and that's used fairly often in trigonometry as the variable, or the input variable for the trig functions. So just something to get used to seeing, that's the variable theta. It's like an x or a t, right? It's just your input variable. All right, so other than that, don't worry about it. All right, so y equals sine of 2 times theta plus pi. All right, so I put up here the key things we need to look for before we just try to graph this function. These are not the type of things where you're like, oh, let me look at this and then just go ahead and draw the graph. You need to think about what numbers you have here and where they are and what they represent before you can actually go ahead and start sketching the graph. All right, so first off, the amplitude. Right, remember, the amplitude is your vertical stretch or shrink, which is a number multiplying in front of the parent function. Well, what number is multiplying that sign? There's nothing there, which means it's a 1, right? It's 1 times sine of all this stuff. So my amplitude here is going to be 1, which means I'm not doing a vertical stretch, right? Because for the regular graph of the sine function, the amplitude is 1, right? It goes from 0 up to 1, right? So it has that amplitude, that height of 1, right? When we're talking about the amplitude, maybe I should make this clear. It's not from the lowest point to the highest point, right? Not from -1 all the way up to +1. The amplitude is from your middle line, right? Your mean value or your middle value up to the maximum value. So it's from 0 up to 1. So the amplitude is 1 for the normal sine function. All right, so my amplitude here is 1. That's not changing, right? So it's not going to stretch the graph or shrink the graph in that vertical direction, right? The period, right? Normally the period for the sine function is 2 pi. What changes that is if I have a number in here multiplying my variable, which I do, right? I have a 2 in there multiplying my variable theta. So the period is going to be my normal period of 2 pi divided by whatever number is in here, 2. And 2 pi divided by 2, the 2's cancel out. So I'm going to have a period of pi, right? Which means for this graph, instead of doing this whole thing between 0 and 2 pi, it's going to get kind of compressed in the horizontal direction. It's going to do that whole period all the way up, all the way down, and back to the middle between 0 and pi, right? So instead of doing that between 0 and 2 pi, we have to squish it together and do it all between 0 and pi, all right? So that's my period. The horizontal shift, right? Horizontal shift is when there's a number added or subtracted to our variable. Theta plus pi, there's my horizontal shift. And remember though, it's the opposite sign, just like with the other rules of, or for the rules of transformations that we talked about with other functions, it's the opposite way. So plus pi actually means we're moving to the left pi units, right? So horizontal shift, I'm going to just put that as negative pi, right? Meaning we need to shift our graph to the left pi units, right? The vertical shift, well, the vertical shift is if we have a number added or subtracted outside of the parent function, which we don't have here, so my vertical shift is going to be 0, right? Like if outside of this parentheses I had a plus 5, that's a vertical shift of 5. Right, but there's no number added or subtracted here, and so I don't have a vertical shift at all. Right, so I'm going to draw the graph of the function here and then talk about the domain and the range of function once we're done. All right, so my amplitude is 1, and I don't have a vertical shift at all, which means my high point is still going to be 1 and my low point is still going to be -1. Right, notice I didn't label the graph at all until I find all this information, because I don't know if I'm going to have to go between -1 and +1, or if there's a vertical shift and I have to move things up or down, or if there's an amplitude where I have to make it go between like -5 and +5 or something like that. So I don't really label the graph until after I find all the information I need. All right, and then I have a horizontal shift of -pi. So remember, the sine function normally starts at the origin, right? That's normally my starting point. Now I need to move that to the left pi units. So now my starting point is going to be over here at -pi. All right, so that's our horizontal shift, and for the sine function, it's starting at the origin. So the horizontal shift, if I take that point, I move it over to the left pi units. All right, and then our period is pi, right? Which means between -pi and 0, that's when this graph is going to complete one full period, right? Because from -pi to 0, that's a distance of pi. That's when we have to complete one whole period. So the way I do this with the graph is I first figure out where my period starts, where it ends, right? Where it starts is determined by the horizontal shift. Where it ends is basically if I take that horizontal shift, -pi, and add the period to it, right? -pi plus pi equals 0. That's where my period ends. And then I cut that up into 4 sections. So I first cut it in half, and then I cut each of those in half. And those are going to be like my guideposts for up here. It's going to start in the middle, and then go up to the highest point, and then go back to the middle, and then go down to the lowest point, and then go back to the middle, and that's going to complete one full period of the graph. Right? And then I can just do that again. So then over here, I go over another pi, right? I do 0 plus pi, which takes me to pi, cut that into 4 pieces, and then I go up to the middle, to the bottom, to the middle, and I do that again. And then I can do it again over here. Pi plus another pi gives me 2 pi. Cut that into 4 pieces, the top, the middle, the bottom, the middle. Do the whole thing again. I can do it again on this side. And once you get a couple periods of the graph, basically you've got the graph of that function. All right, so here's my graph of y equals sine of 2 times theta plus pi. One example of doing these, these rules for the transformations of the sine and cosine graphs, I am going to make another video where I go through at least 2 more examples. Hopefully I'll have time to do 3 on there. We'll see how long it takes. But make sure you check out that next video that I do so you can see more examples where I use some of the other rules besides just the couple that we used this time.